So hello, lovely people on Zoom. We are going to, in this video, go over the resonance structure that we see here. This is the fourth resonance. Oh, I gotta turn on my pen. This is the fourth resonance structure on the worksheet. And overall, I feel like a lot of people were very hesitant on resonance during class. So I just wanted to go over this to give you guys the opportunity to hear another explanation and to practice a little bit more. So hopefully this helps. And as always, if you have any questions after watching the video, you can definitely let me know. So the first thing that I want to point out when I look at this molecule is, well, first I just want to plug on some lone pair. So let's go ahead and put our lone pair on our nitrogen. And on this nitrogen over here, we know that these two nitrogens are neutral because they don't have any charges. And then something else I want to point out is right here at this intersection between the triple bond and the single bond, there's a carbon. So right there, there's a carbon. And I know that in class, a lot of people that did get to this problem, when they were drawing resonance structures, they forgot that carbon, which is totally okay. Resonance structures are hard enough as is. But I wanted to make sure that I pointed that out to make sure that, well, we were all on the same page here. So when we are drawing resonance structures, we want to first identify which atoms actually have p orbitals. So that's what we're going to do. We're going to start out just by determining which of these atoms have p orbitals. So we know that this atom and this atom are definitely going to have p orbitals because they have pi bonds. Same with this carbon and this nitrogen. If we look at this nitrogen over here all the way to the left, we see that this nitrogen is a heteroatom. It has a lone pair. It is adjacent to a pi bond, and it looks like it is sp3 hybridized. So I didn't say it is sp3 hybridized. I just said it looks like it's sp3 hybridized. So since all of those qualifications are met, we know that this nitrogen is actually going to be sp2 hybridized, and it will have a p orbital. So the nice thing about this molecule is that all of the atoms have p orbitals. So we can really move these electrons wherever we want to. So what I'm going to do now is I'm going to erase my drawings, and then we're going to get started. Now remember, when we are doing our kind of resonance structures, we want to start out with an area with electrons. So if there's some place with a negative charge, that's definitely where we want to start out moving our arrows. But if not, we can just start out with one of these lone pairs. So let's try and start out with the lone pair at the top. Now with this lone pair, I have to bring it to this area right here. Now you can't just like take this lone pair and say that you want to bring it over here. You have to bring it to the kind of adjacent bond or atom. But what happens is if I try and do this, let's go ahead and draw that out real quick. If I try and do this, I'm going to get something really wild. We're going to get like a quadruple bond here. And then this poor carbon has 10 electrons. So it exceeds the octet. So this was a failed attempt. This is not going to work. I have to start at the other nitrogen, and that's okay. Kind of part of resonance is just like trying and seeing, okay, does this work? Does something good happen? If something good happens, then continue. If something bad happens, then be like, oh, I guess I'm done here. So we know that this nitrogen, nothing good is happening here. So let's try and start working from our other nitrogen. Here we know that we can take these electrons and move them right here to create a pi bond. But if we're making a double bond in this location right here, our double bond would be right there, we have to break a bond. So we can choose to move these electrons right here and put them on this carbon atom. So let's draw that resonance structure. So we're going to have H2N, double bond, and then we're going to go up like this to a nitrogen, have our lone pair on the nitrogen, and then we're going to have a lone pair right here. So let's make sure I didn't forget anything. H2N, yes, those electrons go there. Okay, that looks good to me. And that's a valid resonance structure. It's not the best because we know that carbon doesn't like to have a negative charge, but it's still a valid resonance structure. Instead of moving the electrons onto this carbon, we could also choose to just move that pi bond. So let's say we move that pi bond right there. Now, if we move the pi bond over, then what happens is, well, this carbon is going to have 10 bonds because, or not 10 bonds, excuse me. This carbon right here is going to have 5 bonds because we're making a bond. So remember, if you make a bond, you have to break a bond. So we made a bond, so we have to break a bond. So what we can do is we can take one of these pi bonds and we can take those 2 electrons and push them on the nitrogen. And then that's going to give us something that looks like this. So again, this definitely isn't the best resonance contributor, but it's still like a relatively decent resonance contributor. Still a valid resonance structure, nonetheless. So we can do that. That's totally okay. What else can we do? So we threw those electrons there. We could also choose, potentially, to add these electrons to the nitrogen. So this is going to be like really wild, because we're going to take and make this a carbocation. So now we have a carbocation here because we're taking away electrons. And we would give this nitrogen a -2 charge. So this definitely isn't a very stable resonance structure, but it is a resonance structure nonetheless. And then I believe that might be all of the resonance structures. Well, I guess we could also move. No, we couldn't do that. We can't do that. So, and then we could also have resonance structures where we push these electrons back on here. Now, the goal of resonance isn't necessarily to identify all of the resonance structures, unless the problem says, like, this molecule has this many resonance structures. Identify them all. Because, like, a resonance structure like the one that I'm drawing right now is just like, this is not going to exist in nature. You have 2 carbocations, and then you have this nitrogen with a -2 charge. What's more important for you to be able to do is to be able to recognize how the arrow pushing should go, recognize what the arrows mean, and then also understand the fact that only electrons that are found in p orbitals can participate in resonance. So if it's not in a p orbital, then that atom cannot engage in resonance. So that's a really kind of the main theme. So definitely keep trying to practice these problems, look at the worksheets, and hopefully collectively they all help to make you feel a little bit more comfortable with resonance. And hopefully this video explanation helped as well. So I think that is all for this video. I hope that this was helpful, and hopefully I'll see you guys soon.